Hello everyone, my name is Xu Wei. I'm going to present our research paper TensileFuzz, a technique for generating seed input via string constraint solving. This is a joint work from Purdue University and the Renmin University of China. Here is a brief introduction to mutation-based fuzzing. Fuzzers start from valid seed inputs and continuously modify them to explore various execution paths. In each fuzzing iteration, a seed input is selected from the seed corpus for random mutations. The mutated inputs are executed on the target application and the code coverages are chased. Those mutated inputs that increase code coverage or trigger bugs are saved into the seed corpus for further mutation. Valid seed inputs play a critical role in fuzzing process. To illustrate, we ran AFL on libzip for 24 hours with and without valid inputs and present the path coverage for both cases in this figure. As we can see, fuzzing with valid seed inputs results in 5 times more paths than fuzzing without. Fuzzers are usually expected to start with good seed corpus to get good results. But what if the program is not open source and the seed corpus is not available? This paper aims to address this problem and facilitate seed input generation in seedless fuzzing. There are existing techniques aiming to get valid or semi-valid seed inputs, including traditional symbolic execution engines like CLE and S2E. Hybrid fuzzing combines fuzzers with symbolic execution engines or gradient-based search engines, also helps generate seed inputs. We use libzip as an example to explain the limitations of the existing techniques. A valid zip file consists of 3 kinds of data structure, including EOCD, end of central directory, CDH, central directory header, and LFH, local file header. During process of handling an archive, libzip performs multiple checks on different fields of the input file to ensure validity of the archive. Here, we list some of them. Check A examines on the magic number. Check B examines on the length of remaining data. Check C examines on the offset of the EOCD structure and the value of CD size and CD offset fields. Check D is a for loop, which convolutes offset, length, count, and magic number. Some checks are easy for vanilla fuzzing, but some are not. For example, check B constrains the remaining size with a value extracted from the input file. Randomly mutating the input bytes or extending the file size are unlikely to satisfy the check. Symbolic execution can help with this case, but still get stuck in other checks. Consider check C, whose left-hand side is affected by the values extracted from the input file, and the right-hand side is affected by the offset of EOCD derived from the loop predicate at line 3. Such a check can be satisfied by either decreasing the left-hand side value or increasing the right-hand side value. In general, it is difficult for symbolic execution tools to directly reason about the offset semantic, because increasing EOCD offset requires increasing the loop count, which is of low priority for symbolic execution engines. It is more likely that the left-hand side variable, such as CD size, is set to a very small number to satisfy check C. This would result in the failure of check D at line 9, because it requires a larger value of CD size. As a result, none of vanilla fuzzers, symbolic execution engines, and hybrid fuzzers can pass check D in this case. From this example, we can observe that there are many string constraints in programs, including offset, length, and count. which are not easy for existing techniques to reason about. However, we found string solver particularly suitable for handling such constraints, and the input is a string by its nature. So we consider explicitly model string constraints for inputs, instead of using low-level per-instruction modeling. Here is the workflow of TensileFuzz. It is built on top of AFL. For a seed selected from AFL seed corpus, firstly, TensileFuzz groups consecutive bytes whose mutation affects the same set of predicates into an input field. Given the field information, TensileFuzz tries to construct constraints, including both string constraints and path constraints. The two sets of constraints are linear constraints and passed to SMT solver to get a solution. If SMT solver fails in generating an input, the gradient descent search is then applied to satisfy nonlinear checks. Otherwise, the generated seed is validated and then added to the input queue for further processing. TensileFuzz does not require the source code of the program under test. It runs the program executable on a modified QEMU. Here are more details about how to construct string constraints, including length, offset, and count. They are constructed by observing the changes in read system call. For example, if we change the value of CD size from 62 to 63, the bytes affected by the system call is changed from 62 to 63. We are then convinced this field is related to length. And we can further construct a constraint saying the value of this field should be equal to the length of all the fields starting from 42 and ending at 83, which is the length of CDH structure. The T here denotes a real field in the input, and P is the padding, which means the potential place to extend the length. TensileFuzz extends length by instantiating the padding. Similarly, if we change the value of CD offset, we observe the position read by system call is changed from 42 to 43. We then conclude the field is related to offset and construct the constraints, which means the value of CD offset field should be equal to the start position of CDH. The count is a little bit different. By changing the field n entry at position AE from 2 to 1, we can observe the system call count is reduced from 2 to 1, and we learn this field corresponds to count. Then we can construct the constraints that the CDH structure contains 2 entries. The string constraints draw the frame of the input, and we still need to fill in the value for each field. We call the constraints collected from predicates and the path constraints. We use linear regression to build path constraints. The predicate values are affected by several fields, and we keep mutating these fields to get the sample value of left-hand side and right-hand side for the predicate. We assume the expression of left-hand side and right-hand side are linear, and calculate the coefficient for each field. In this example, we can learn the left-hand side is affected by tk and tk plus 1. The expression of left-hand side is the value in tk plus the value in tk plus 1. The expression of the right-hand side is a constant, which is A4. Combining expression with the predicate operator collected from QEMU, we can determine the path constraint for predicate D. Path constraints are based on probing and sampling, and thus is not sum nor complete. We resort to an external iterative procedure to mitigate the consequence of incompleteness and unsoundness. In particular, for a new path to explore like line 4 in this example, we construct a set of constraints as mentioned earlier and pass them to SMT solver. In this example, we start with initial value x equals 6, and the constraint for the line 3 is 3 times x greater than or equal to 20. If there is a solution, we execute the path with the solution and validate that the intended path is taken by the input. However, x equals 15 does not reach line 4, because now y equals x as branch in line 2 takes false. In this case, we will reduce the field probing and the constraint derivation with the new input. Passing 15 to the program, we generate path constraint with x greater than or equal to 20, and get a solution x equals 25, which can get to line 4 now. Next, I will discuss the evaluation results. Our evaluation is conducted on 2 benchmark sets, including 12 real-world programs that are widely fuzzed by other fuzzers, and the Google Fuzzer test suite. We compare with 4 state-of-the-art fuzzing techniques, including AFL, the most popular vanilla fuzzer, QSIM, which combines symbolic execution with fuzzing, and 2 gradient-guided fuzzers, Angora and its improved version SLF. We performed 2 experiments. The first experiment showed the capability of seed generation and the path coverage. The second experiment shows the bug finding capability by measuring the time of each tool to reach the buggy point. The first set of experiments is on the 12 widely fuzzed programs. We run each testing tool on each program for 24 hours and choose the median of 5 runs. The experiment results are shown in these figures, whose x-axis represents time and y-axis represents the number of covered paths. From these results, we can make the following observation. First, AFL does not work well without valid seed inputs in most cases, because it gets stuck in finding the first valid input and cannot proceed. QSIM achieves reasonable performance, but still does not work as well as TensileFuzz, since it does not explicitly model constraints related to input growth. Gradient-based fuzzers are good at arithmetic checks. For example, Angora achieves much better results in lane, the figure E, than other programs, because there are lots of arithmetic relations in lane. However, interdependent checks may prevent them from exploring deeper paths, because the gradients may disappear when they go deep. TensileFuzz achieves the best performance and reaches good coverage in a much faster pace in most cases. It does not work well on lane, which is an MP3 player, because MP3 format has many bit-level growth-related constraints, which are not currently handled. Another set of experiment is on the Google Fuzzer test suite, which takes some locations to see if a testing tool can reach these locations. In total, we evaluate on 14 locations. In the table, TO means timeout for 24 hours, and NA means the tool does not work on the program. Angora does not work for libgpack because it fails taking some instructions. We can learn AFL can only reach 6 locations, while QSIM and SLF are slightly better and reach 7. They always take a very long time to reach locations compared to TensileFuzz, though Angora can reach locations in a much faster pace. It reaches only 5 locations, while TensileFuzz reaches 12. TensileFuzz can reach all the locations reached by other tools with less time, and even reach 4 extra locations, which are not reached by other tools. In conclusion, we developed a novel seed input generation technique for mutation fuzzing, which can automatically grow the input while respecting the intrinsic constraints across input fields. We propose the novel idea of treating binary fields as string variables and explicitly modeling important cross-field constraints as string constraints and linear relations between fields as path constraints. We develop a prototype TensileFuzz and evaluate on 12 real-world applications and achieve good results. Finally, our tool will be available at our GitHub repo. Thank you for listening to my presentation.